Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon. Um, we still have a lot of people missing, but anyhow, I'm gonna record this lectures. Therefore, I'll just start. And for those who actually missed the early part of the lecture, you can just review the recorded lectures again. Okay. All right. So because I'm at home, so normally when I give you guys a lecture, and if I'm at the office, what I would normally do is I would have a PC in front of me and I'll be teaching using iPad so that I can just draw and whatnot. But since I'm at home and my PC is actually at the living hall, so I cannot actually stay there because otherwise you'll be hearing some other background noises. Probably my son wants to talk to me and so on and so forth. So if in case if I'm doing this lecture and then say for example the slide did not update, please shout. Don't just press the raise hand button. Please do let me know that the slide was not updated and so on and so forth. Okay. All right. So so the original plan is for us to actually finish all the lectures on peptides last week. Okay, but instead of well, during the weekends, I was looking through again all your course learning outcome, and I noticed that I did not cover one topic about peptides. So that's what we're going to do today. So today will be the last lecture about peptides. On Thursday, we're gonna start learning about ribonucleic acid, and the lecture note on that particular topic have already been posted on Spectrum. Okay, so we'll just use what we have. And of course, due to frequent holidays, and then we had two tutorials or two quizzes, and then we had one live tutorial. So pretty much all the lecture slots have been like filled up. Thus, the nucleic acid section that you guys will be learning on Thursday will pretty much covers up like very basic information or knowledge about what nucleic acids are and how do you actually look at the nature of nucleic acid and so on and so forth. So we'll leave that on Thursday. So what I'm going to do today is I'm going to try and finish up all the chemistry bit about peptides. And then if we do have extra time, what we will do is we'll just let you guys, it will be a free Q&A questions. If you guys want to ask me about anything related to peptides, then you can. Because next week we're going to, next Thursday, we're gonna look into nucleic acid, and then next Tuesday we're gonna have our second lecture of nucleic acid, and then on Thursday next week we will have our second quiz. Okay, so it's already, or today is already, or this week is already on week 13. So we don't have extra time to actually, have another discussion, live discussion, and so on and so forth. We'll think about that again once we have covered everything and once we have gone through your quiz. If you want to have another session, well, it won't be a compulsory session, of course. It will be just an open session whereby we will talk a little bit on the quiz. We'll discuss a little bit on the quiz, and you can ask me anything before you do your exam. Okay, so I've already prepared all the exam questions. Dr. Dini also have prepared everything. So it's just a matter of time to have your final exam. Okay, so because we will not have any other asynchronous lectures, this will be kind of like the closure survey for that particular section. Okay, basically on the asynchronous lecture, what I did was embedded video learning. This will be like a summary on what do you think is best, what's your expectation, and whether the learning using the embedded video actually cater what you wanted for your learning. Okay, so please just quickly go to and scan this one and help me in answering the survey, because it's really helpful if you can actually do this. It will be helping me and my colleagues, and of course UM in general, because this program that we are using is part of your spectrum, your learning spectrum application. So if it's actually useful for this group of students, then we might promote this program so that all other lectures will be using the same method for asynchronous learning. Okay, so link for today's attendance, just quickly QR code this, and the code is the last lecture. Of course, it's not the last lecture, it's just the last lecture for peptides. Okay, all right. So that's enough about mumbling. Now, so before we continue with our lecture, let's move back to what we've learned so far. Okay, we've looked at primary structure, secondary structure, tertiary structure, quaternary structure of proteins and peptides. Okay, so by now, hopefully, you'll be able to identify what are the primary structure of a protein or peptides, what are secondary, what are the differences between the 2 or 3 examples, or pretty much 2 examples of secondary structures that we've touched, that we've covered in the lecture, what makes a tertiary structure, okay? So secondary structure, you only have one 3-dimensional structure of a peptide or protein, but once you go up to a tertiary structure, you need to have at least 2 of the secondary structure interacting in some form, okay? And when you move up another layer again to quaternary structure, it's pretty much you have 2 of the tertiary structure within 2 different polypeptide chains interacting to one another, forming a protein, a functional protein, then you call it as a quaternary structure. Okay, hopefully by now you already memorized everything. And we've looked at and sub methods that can be used to identify protein sequence. Okay, so this is what we're going to do today. That is the part that I actually missed because I thought I've already covered, and when I looked back all the lectures, I actually did not cover any of these aspects. So what we did so far was moving forward from primary, secondary, tertiary, quaternary. So what we will do today is to look back, what if you have those 2? Can you actually go back to here and here? Well, pretty much mostly going to the primary structure and not so much on the secondary structure, even though you can do that, but we don't have time to actually cover about that topic. Okay, so throughout this lecture, we will use a model protein. Again, the protein of interest that I like to use is insulin because it's a protein and then it's small. It's not that big. Okay, so the criteria that you need to remember for an insulin is that it has 3 disulfide bonds. Okay, I will show you guys soon. And then it has 2 peptide chains or backbone. So that is the structure of an insulin. So these 3 over here are highlighted in blue, black, and red are all the disulfide bonds. Between the 2 chains in green, how did it go? I think it's like that. Okay, and in cyan. Okay, so there are 2 peptide chains connected via 3 peptide bonds. So these are a good example of a quaternary structure of a protein. Okay, now, so if you have an insulin, say for example, you don't know that it is an insulin. Okay, so how do you actually, what are the processes that you can actually do to make sure that you be able to identify what is the unknown? Okay, so this is the general step that you can take if you have any unknown proteins. Even if you do have a known protein, but say for example, you know, insulin has this type of sequence. Okay, it has 2 chains, it has 3 disulfide bonds, and then of course, based on the previous lecture, we know that it has a specific primary sequence. Okay, primary structure, which is the primary sequence of the insulin. Now, how do you, if say you want to manufacture it, okay, one of the cheapest way to manufacturing a protein is by using a microbes, okay, a microbial bacteria, or a common ones that people use is called as E. coli. Okay, we might have encountered this during your high school. Can't remember, but I think I did during my years. But yeah, anyhow. So one of the ways by which you can produce a protein in large scale is by using a bacteria called E. coli. And once this bacteria, so you know, you need to play with genetics, you need to play with nucleic acids and so on and so forth to actually develop this E. coli so that it can produce the protein that you want. Sorry. So how do you actually know the protein that being produced by E. coli is an insulin? Okay, so that is one of the things that you can do if you are to understand what this today's lecture is all about. Okay, so the topic that I'm focusing on is determination of a primary structure, not secondary, but primary. Just focus on that. So first thing first, before you do anything on the analysis of the sequence of the amino acid, what you need to make sure is you need to first denature the protein. Okay, so denaturing of the protein and some proteins, for example, insulin, if you just simply want to denature it using heating, for example, you might need to heat it up very, very high to break the disulfide bond, right? Because as I mentioned previously, disulfide bond is one of the strongest after covalent bond. Okay, so you need, if you want to denature a protein, because it's an unknown protein, you might want to break down the disulfide bond. That's the first one. Okay, so that's why I put it here as number one. So to break this bond, okay, so you need to reduce or break the disulfide bonds to obtain a linear chain. So that is the first key. So to break it, so basically that's an example of a disulfide bond. You use a reducing agent such as mercaptoethanol, and then you pretty much break the bond into two cysteines which are not connected to one another. Okay. At the same time, if you what you do next is if you just break it, okay, in the lab, for example, so you put into mercaptoethanol, you stir it for a while, you know that the bond breaks, but and then you just simply do an extraction or column chromatography and so on and so forth to actually get a pure sequence. But if you just do that, what might happen is that we have oxygen presence in our atmosphere. We might have dissolved oxygen in the solvents. So some part of it will start to oxidize again, forming the disulfide bond. Okay. So what you do is first step is to reduce it. Well, the second step is to stop the oxidation from happening again by oxidizing it using iodoacetic acid, for example. Okay. We should block oxidation using iodoacid. Okay. So once you have that, then the structure is more of a methionine. Okay, so methionine has a thiol group and then ethyl at the very end. Okay, so this one is the amino acid. Now, it doesn't mean that once you have formed an oxidation, a high oxidation number of the thiol group, it will not like react at all. It can, but it will be a much harder process because it needs to be reduced first and then it needs to be oxidized to form again the disulfide bond. Okay, so we just simply use iodoacetic acid, block it, and then we'll just proceed with the next step. Okay, so by doing this, you now be able to break all bonds, and by using a purification step, you can now isolate the two chain, okay, chain A and chain B of the insulin. Okay, so the example is insulin. All right, so this is pretty much more or less the same thing as what I've just said. So you break the SS bond to allow separation or purification of individual chain, use mercaptoethanol and iodoacetic acid, and then you can separate the A and B chains. Okay, so those are in primary sequence. Okay, so those are the two chains of an insulin. You have the top chain, chain A, and the bottom chain, chain B, interconnected via two disulfide bonds between the chains, and then one disulfide bond intra-chain. Okay. All right. So now once you have the linear sequence of peptide, okay, so there are multiple ways by which you can now try and identify the sequence of amino acid. So we will look at that all the examples and how you can actually do it chemically, because we are all chemists. So here we go. The first one is you can analyze the number and kind of amino acid in a peptide chain by a full, okay, hydrolysis of the amide bond. So you need to notice, take note of this. So there are multiple ways to do it. So this one is the full hydrolysis. We have a partial hydrolysis, and then we also have an enzymatic hydrolysis. Okay, so those are the three main categories, but of course, each category have its own sub reactions that can be done underneath there, which will cover some of it, and we will not cover. Of course, we will not be covering everything. Okay, so the first one is a full hydrolysis, and to do that, for example, if you just take a chain A, of course, it needs to be, as I mentioned, fully linearized, denatured. You simply just chuck it into a beaker of 6 molar hydrochloric acid, warm it up. Of course, you need to stir it, leave it for 24 hours, and what you will get is amino acids. Okay, so everything else, okay, so it's pretty much the basic hydrolysis of an amide bond. Okay, so you have an amide bond, like that. Then if you do any acid catalysis or hydroxy or base catalyst, so it will react slightly differently, but what you will do is pretty much towards the end of the day, you will break this bond. Okay, and even if you have a multiple bonds, because you are using a highly concentrated hydrochloric acid plus heating, and of course you need to leave it some time. It's not instantaneous because amide bond is one of the non-reactive bonds, so it takes time to actually activate the bonds and break it apart. Okay, all right. So and once you have all the amino acids, so you convert it from a protein or part of a protein, convert it into an amino acid. So what you need to do next is need to analyze. Okay, and the basic principle of analysis in any biology, the easiest one that we normally use is this guy over here. Okay, this is what we call as HPLC, or high performance liquid chromatography. So it's pretty much like your column chromatography, but instead of just using a column chromatography, it's an automated system. And what you will get over here is basically a spectrum of your amino acids. Okay, so well, of course, the analysis itself does not straight away tells you what amino acid you have. Okay, so for example, what you would do is after you hydrolyze everything and then you run it on HPLC, this is what you will see. Just this, not the one at the bottom. Okay, and of course, during your run, you do not have all this information. Okay, this, you don't have that. Well, I actually use the standard graph, but anyhow, it's the same thing. Okay, so once you have your spectrum, okay, what you do need to do next is to actually run a standard of amino acid. So because we have 20 naturally occurring amino acids, so if you were to identify an unknown protein, what you need to do is you need to run every single amino acid using same column chromatography. Okay, so HPLC, similar to a column chromatography whereby you have a silica, right? So HPLC also have its own silica column. It's an official column that you can buy, normally made up of either a PEEK material or polymer material or a stainless steel. Okay, so you have a column inside here whereby the molecule or the amino acid will be separated based on the type of column that you use. Okay, if you are using a hydrophobic column, then of course hydrophobic molecule, for example phenylalanine, will be retented more in the column. Therefore, so this one is over time. Okay, therefore if you have a hydrophobic column, phenylalanine will come out later. Okay, so this molecule will come out fastest, and the ones over here will come out the latest or slowest. Okay, this example over here, of course, it's not a hydrophobic column. Probably something like a polar column because arginine came out the last. Okay, arginine is polar, it came out the last. Polar charge, of course. Okay, so well, of course, because I've already drawn a spectrum like this, it should be the other way around. This one is a sample. Okay, you might see something like this. And then because you have your standard, because you ran your standard, you can actually compare directly at this particular retention time what is the amino acid corresponds to. Okay, so by doing this, what you will do know is you will know that your protein of interest or your unknown protein contains this and this and this and this type of amino acids. Okay, so by knowing that, so for one thing is you can actually do further analysis very easily. So say for example, if the example listed here does not have any cysteine. Okay, so in the future, if you were to repeat the same experiment, you now do not need to do the first experiment using mercaptor ethanol and iodoacetic acid. Okay, so now you can skip some steps to do your analysis again. Okay, so but in general practice, normally we just do it because first thing is an unknown. Nobody reported what are the amino acids available in the protein. So you just need to make sure that you follow the general procedure so that you can cover as much as possible. All right. So now this is the first step. So this step by no means illustrate the coupling or bond or the sequence of the amino acid again, because towards the end of the day, you are cleaving off all peptide bonds or amide bonds. So it becomes individual amino acids. Therefore, you will not be able to know the sequence. Okay. So you need to do additional process to completely identify the protein sequence. It's very tedious to determine protein sequence via chemical processes only. For example, the ones that I'm showing you here, if you do a full hydrolysis, you will not be able to do it. Okay, you will never be able to identify the correct sequence. That combination using biological enzyme to ease the process is normally being done. Okay, so this is what we're going to do. So what we will do next, since we've did reduce all the disulfide bonds, we cleave off all the amide bonds. Now we know what are the amino acids in there. Now from the number of amino acids, you have two options. You can either proceed with a chemical partial cleavage or a biochemical partial cleavage. So biochemicals is using enzyme. Okay, so you might ask me, then Doctor, what's the need of doing second step, a full hydrolysis? Now, the full hydrolysis is very critical for the enzyme because as you will see next, enzymes normally have a very specific sequence that it needs to identify before it can actually cleave off. Okay, so say for example, if your sequence has alanine and then serine, okay, and glycine, something like this. And you know that enzyme A, okay, enzyme A cleaves only at sequence A and A. Okay, so it only cleaves off at this particular sequence and no other sequence. So because you know that your protein, your unknown protein contains a high quantity of alanine, then you might want to try and use enzyme A to do your partial hydrolysis. If your unknown, that once you have done your full cleavage, do not contain any alanine, then you do not need to do a partial hydrolysis using enzyme A because you will not get anything. Okay, I hope you understand what I'm trying to say here. Okay, so the full hydrolysis is still important to do for an unknown. If it's not an unknown protein, then you might not need to do it at all. But of course, nowadays we do have advancement in spectroscopy, for example, NMR. So as long as your unknown protein is pure enough, you can simply just chuck it into the NMR machine and you can be able to identify the sequence of the protein rather not that easy. It's really difficult, but you still be able to do it without doing all this chemical hydrolysis. Okay, all right. So moving back to partial hydrolysis, so what you do is you want to break down a large peptides into smaller fragments. So say, for example, the insulin that I give you is a good example of not needing to do any perhaps full hydrolysis or selected partial hydrolysis, because the sequence itself is rather short. It's not a very, very long amino acid. But say if you have what kind of protein that we've learned? We've learned about hemoglobin. Okay, you know hemoglobin is a quaternary structure, so it has at least 4 different peptide sequences. Okay, so it must contain a lot of amino acids. So what you can do is you can actually do a partial hydrolysis to break down the larger molecules into smaller ones, so that it will be easier for you to actually analyze. Okay, so an example over here, of course, if you, I won't be able to use hemoglobin because hemoglobin is very, very big. So it will be very massive to actually show you guys an example. So what we'll use here is, for example, if you have a chain A of the insulin, which has 21 amino acids, so you want to break it down to about 5 or 6 amino acids segments, so that towards the end of the day, it will be easier for you to analyze using not just HPLC, because HPLC, you need to know the sequence, because different sequence, for example, a triple alanine, okay, will have a different retention time than if you have a 2 alanine with a serine attached to it. Okay, so this one will have different retention time. So you cannot simply just use HPLC. But what you need to do is you need to use liquid chromatography mass spectrometry. That's the bare minimum. Okay, so mass spectrometry is equipment that was founded like how many years ago? I can't remember. About 50, 60 years ago, compared to NMR spectroscopy, which is rather recent, about 30 years or so. So mass spec can be used for a very, very high throughput screening of protein sequence. But to actually use that, you need to make sure that the amino acid is rather short, not that long. If you just shoot in 21 amino acids, then the probability is so big. But if you cut it into 5 or 6 amino acids, or probably shorter, what you can do is, let's say, for example, that one is 21 amino acid. Okay, so if you cut it into 5 or 6 segments, like this, so there will be a higher chance for you to be able to identify what is the amino acid here. Okay, and what you can also do is run it multiple times. So this is the first run. Okay, this is what you get, and then your second run, probably you'll get a bigger pieces like this. Okay, so if you get a bigger pieces like this, and you manage to actually identify, oh, this sequence and that one is the same. Okay, and now because of the overlapping, because of this peptide sequence is like it's connected in a bigger piece. Okay, and while the first run is a smaller piece. So what you can do is you can minus the mass of this whole thing, and then whatever mass remains here might correspond to the mass at this particular region. Okay, I'm not sure if you can understand what I'm trying to say here, because I'm trying to catch time, and I've been doing this for a while. So if you don't understand about something, do let me know. Okay, so it's very, very critical for you to tell me that you don't know. Don't just simply keep quiet. Okay, so the resulting mass or fragments are then separated, and then the amino acid composition of each segment can be determined using electrophoresis or an amino acid analyzer. So amino acid analyzer, we will talk about it in the next few slides. And of course, mass spectrometry. Okay, mass spectrometry has been modernized in a very good way. You can do MSMS, for example, a tandem mass spectrometry, whereby you'll be able to identify what is the mass for the whole thing. And then you will ask the mass spectrometry to break down from this one big chunk into a smaller chunk, and you'll be able to identify the mass. And from there, you can get like a snapshot of each individual short segment of amino acid, then you can kind of like putting in as a puzzle and finally be able to know the whole sequence of your chain A amino acid, for example. Okay, so of course, you don't just do it once. As I mentioned, you need to repeat it multiple times, not just two. You probably need to do like at least 5 or 6 times to be able to actually do it. If you were to use this method, if you just use the different methods like mass spectrometry or NMR spectroscopy, then you just do it like once normally, and you need to spend more time to actually analyze the data rather than doing the experiment itself. Like this one, you need to do the experiment. Okay. All right. So there's 2 ways of doing this: chemical and biochemical or partial hydrolysis or cleavage. So we'll look at both 2 examples. The first one is a chemical partial hydrolysis. You have 2 options. The first one is to use a dilute acid with short reaction time. So before this, you use 6 molar of hydrochloric acid. Okay, 6 molar HCl, and then at 100 degrees temperature for 24 hours. Okay, and then if you do this, you know that you do full hydrolysis. So if you dilute it even more, so say for example, just give it an example. Okay, 70 degrees, probably in 3 hours. Then of course you will not get a full hydrolysis, and you'll get some segmentations. Okay, so it's still the same thing, simply a base acid and base amide hydrolysis. It can be controlled using cold solution. You can vary the contact time, you can vary the concentration of the acid, vary the temperature, but it is still not preferred as the cleavage is too random. Okay, so a little bit of disadvantage, but this is how our forefathers actually use this technique to identify protein sequence. So that's why I'm just gonna touch it a little bit. Okay, so it's no longer used in our modern world. So the second method, which is still usable, is doing a partial hydrolysis using cyanogen bromide. Okay, it's a controlled cleavage at carboxyl group of methionine, very specific. Okay, so non-specific to amino acid sequence as long as methionine is present in the N-terminal site. Okay, so meaning that if say you have methionine at the C-terminal and then some other sequences, then this second option is not feasible. Okay, but if you do have methionine somewhere in the middle, then it is still useful. Oops. Okay, right. So dilute acid with short reaction time, mechanism of reaction. I'll just skip this. I'll leave the space for you guys to actually draw what is the mechanism of acid and base hydrolysis. And if you want to discuss with me whether your mechanism are correct or not, be my guest. We can have a discussion later on. But for today, we're just gonna skip because we only have like about 15 more minutes. Okay, so this is the mechanism of cyanogen bromide hydrolysis. So you have over there, that's the methionine. Okay, you have sulfur and then to at the terminal of the sulfur, you have a methionine. Okay, so sulfur being the nucleophile, trying to find its mate, which is oops, sorry, I need to change my mic. Me. Right. So you have the thiol group going into a delta plus, not really a full carbocation. Okay, it's just a delta plus, and then you have a bromide as a leaving group. You'll get thiocyanogen linkage. Okay, and then you have some rearrangement of your structure in there, forming a furan functional groups or furan ring, while having a methyl cyanogen as the leaving group. Okay, in the presence of this one is just showing you as an acid, so it doesn't have to be HCl. It can be anything as long as there's a proton available and some water. What you can do is you can actually simply cleave off this bond, okay, and then you'll get segments. So you have one segment over there, and then another segment over here. Okay, so the more methionine that you have in the structure, then the more of these cleavage sites you will get. And then the more cleavage sites that you will get, it will be easier for you to actually put them as a puzzle or like a Lego, and then finally be able to identify what are the whole sequence. Or at least by doing this, what you can get is, imagine if this one is 21 amino acid, okay, and if you have a methionine over there, so say that one is 6, for example, the rest is 15, okay, you can easily go and analyze this using either electrophoresis or mass spectrometry and be able to like at least get a very close sequence on the 6 proteins, 6 amino acids. Okay. All right. So that's all for partial hydrolysis in chemistry. In enzyme, as I mentioned previously, there are multiple enzymes that you can actually use to promote hydrolysis, and the enzymes are listed here. Okay, so the good example or common example is pepsin. You might have heard during your biology in high school. For example, pepsin breaks down our proteins. Okay, but it doesn't just break down all proteins. It has a more specific requirements over here. Okay, so pepsins, it breaks down if you have X and Y sequence. X can be any amino acids, non-specific, but aromatic and hydrophobic amino acid preferred, and Y can be any amino acid. So pepsin is generally just breakdowns all, but of course there are preferences. Therefore, if you adjust the time it takes, contact time between your enzyme and your peptide sequence, then of course you'll get a different segments of proteins, okay, or different segments of peptide chains. That's a better word to choose. Next one, you have trypsin. Again, trypsin is slightly more specific. Okay, so it prefers to have an arginine or lysine on the X on the left, and then a Y, which is non-specific. Okay, so Y can be any amino acid, but as long as you have arginine and lysine, then it will cleave over there. Okay, so I think I give an example in the next slide. And chymotrypsin is as you mentioned over here. Okay, so there are other enzymes that you can actually use, and you can actually go to this link to look at some other examples. Of course, whatever link that I give you, you just need to, as a get to know basis, you don't really need to go and memorize it. Okay, it's not covered in the exam or even quizzes. All right, but it's just a good to know basis on what other examples of enzyme that you can use. You might be interested in knowing them in the future. Okay. All right, so as it catalyzes the hydrolysis of one or specific types below, as I mentioned, illustrate a cleaving site. Okay, so that one is the cleaving site, pretty much is in the middle. And proline, no cleavage between two proline residues. Okay, so pretty much enzymes do not really like two prolines. So between two prolines, there will be no cleavage. But say, for example, if you have an alanine and proline, and then say, for example, a proline and serine, for example, okay? So the enzyme might be able to cleave here and here, leaving a diproline intact. And then this diproline can be hydrolyzed either on its own or on its own, as in an acid or basic catalyzed solution. Okay, so we have a lot of acid in our stomach, or more alkaline in our intestine. All right, so most enzymes will not hydrolyze the peptide bond if, okay, so if you look at your lecture notes, it says here protein, right? So so it's a typo. It should be a proline, not protein. So you might want to go and change that. Okay, if proline is at the hydrolysis site. So most protein does not prefer a proline. Some do, some doesn't. So an example over here is a trypsin will not cleave lysine and the proline. However, a chymotrypsin will cleave, or will not cleave as well. but chymotrypsin prefers something like this. Okay, now did I mention? Right. So there are some other enzymes. So it's not listed here, but there are some other enzymes that actually cleaves off protein, proline. But of course, not between two prolines. Again, two prolines is kind of like a no-no. But if it's a combination, then some enzymes do. Okay, so these enzymes are specific to the amino acid sequence. To a lock is specific to a key. Okay, so similar to a lock and a key, so it's highly specific. All right. I'm not I can't remember whether I'll be teaching this subject or not. So, but if you guys are taking natural products and biotechnological chemistry, then I'll be teaching you guys about enzymes next. All right. So, however, for chemicals, if you do have a similar sequence, you can cleave using cyanogen bromide. So sometimes it's just good to just combine both methods. Probably you'll use cyanogen bromide first to actually cleave off all sequence containing methionine, and then purify individual sequence, and then do enzymatic cleavages to be able to identify what are the sequences available. Okay. Just trypsin again, just an example. I'll just keep that one because we don't have time. Okay, so partial hydrolysis. So in practice, how does it work? Again, if you look at your arrows, the arrows are actually different. Okay, so these are, well, something went wrong when I was swapping between a Mac and a PC. So this one is the correct path of the arrows. Okay, so please correct them in your lecture notes so that you will not get confused. All right, so now we've know a little bit about ways by which you can cleave off peptides and whether it's chemically or enzymatically. So how can you actually use that? So how can you actually use the information? So this is how you can do it. So for example, if you do have a short peptide like this, okay, if you use firstly a trypsin, so trypsin likes lysine or arginine, so it will find a sequence containing lysine and arginine, and it will cleave off that sequence over there. Okay, so by cleaving this off, now you will have three different shorter sequence. Okay, if you will be able to identify the sequence, purify them, then you definitely will know that okay, we have one sequence. So originally 1 2 3 4 5 6 7 8 9 10 11. So originally you have 11. 1 2 3 4 5 6 7 8 9 10 11. But now once you treat the enzyme or the peptide sequence using an enzyme trypsin, suddenly you get three shorter sequence. Okay, so from here you know, because it becomes three, then you have two by which it's either lysine or arginine. Okay, now from knowing nothing, then doing just one partial hydrolysis using trypsin, you already know that your sequence now at least it contains two. Okay, but it can be arginine arginine, arginine lysine, or lysine lysine. Okay, so by just doing one experiment, now you know your sequence contains these two types of amino acids, or contains 2 out of 11, either arginine or lysine. Okay, so now you just need to identify the remaining 9. Okay, and to identify the remaining 9, now you want to try something else. You want to try a chymotrypsin. Therefore, you again take the whole sequence. Okay, so that's the 11 amino acid. Treat it with chymotrypsin. It becomes 3 sequence again. But now, because chymotrypsins prefer something that has an aromatic, then you know that, oh, okay, so now you have another 2 out of 11 which are aromatic. Okay, so aromatic can be tryptophan, okay, or phenylalanine. What else? I think these two are the biggest contribution to aromaticity. Okay, so now you know, so just from these two reaction, you now know that you have 4 out of 11 sequences. Okay, you know the amino acids already, you don't know the sequence, but you know the amino acid. But If you now take these two information together and plug it in, so you might be able to finally get something like this. Okay, so be able to validify your sequences using two different enzymes. Imagine this is just two enzymes, but if you have multiple types of enzymes, or if you combine the enzyme partial hydrolysis with cyanogen bromide, then of course you'll be able to have more information that you can puzzle out and be able to get your information. Okay, so that's how you do it. So the most important thing is Ekman degradation. It's one of the ways by which one amino acid at N terminal will be cleaved off per reaction. Okay, so this is the widely used technique even nowadays, and this is what we call as amino acid analysis. Okay, so in the previous few slides I mentioned I'll talk about amino acid analysis soon. So this is it. Okay, so basically what it does is you have your polypeptide, you treat it with a phenyl isothiocyanate, or we call as PITC, okay, or also known as Ekman reagents. So PITC will react with N-terminal amino group, so it only reacts with this one. Okay, even if say you have a lysine, it doesn't really do anything. Okay, so it will react and then it will go unbound. But we will look at the mechanism in the next slide, resulting in thioazolinone derivatives. And this derivative is cleaved from the polypeptide and the mild acidic condition, leaving behind a polypeptide with one less amino acid. So that is very critical. So each step, if you do it in 1-to-1 ratio, of course, if you do it in 2-to-1, then you will get something else. But if you're doing it 1-to-1 ratio, then you will only get one amino acid cleave off per reaction. Okay, so these are the mechanism. Sorry, and it's non-specific to any type of amino acid, as long as the N-terminal is a free amine group, then it will work its magic. Okay, so you have this, and then mild acid over here, then you'll get your thioazolinone derivatives, and this thioazolinone derivative in the presence of base will produce a PTH amino acid, and this PTH amino acid is very stable. Not very stable, it's just a stable chemical, and then this chemical can now be used to identify what amino acid is at the N terminal of the peptide using HPLC. Okay, again using HPLC, if you have that's your Ekman, and then you have your standards like that, or multiple run of standards, you can just mismatch or these standards at this retention time equals to the sample retention time is equals to your standard retention time. Therefore, you know that your sample is actually that particular amino acid. Okay, so you can just read through about how the mechanism works. It's very self-explanatory. Okay, but amine degradation is a very good technique whereby it was shown that you will be able to analyze at least 50 successive sequences in one single run, meaning that you just do it once, automated, so the automated system will just cleave off one amino acid at a time. Okay, and 50 has no issues at all. All right, so this is just an example on how the system works. So it will first cleave off the N-terminal amino acid, then you will inject this into HPLC, and HPLC will say, the sequence is actually cysteine. So well done. Then what you do next is you do another process of cleaving. So and again you have the PTH of tyrosine, HPLC, and then from HPLC it says it's a tyrosine. Okay, and so on and so forth. So that's how you actually kind of like chew up one amino acid at a time, and each amino acid will be compared to a standard. Therefore, you will be able to identify each individual amino acid. Okay, The fifth technique that you can do is you can chew up from a C-terminal, but this method is not really it's not really of advantage. Okay. Sorry. Cannot talk anymore. But anyhow, it's not really of an advantage because it's still useful, but not as much as amino degradation, because amino degradation can be automated and so on and so forth. Okay, so it's pretty much using an enzyme, carboxypeptidase, non-specific enzyme. The issue is the hydrolysis differ from one amino acid to another. Okay, so I'll just skip that one. You can just read it. It's just talking about the enzymes. But what's important is that the rate of hydrolysis is different compared to admin. Admin is a chemical, full chemical. Therefore, the rate of hydrolysis is more or less the same. But for this carboxypeptidase cleavage or partial cleavage, it's not as much as not as good as admin degradation. Okay, so during analysis, the appearance of free amino acid is monitored similarly to admin. Okay, in theory, an amino acid whose concentration increase first should be at the C terminus, because you are cleaving it at the C terminus. Okay, so you know that if HPLC says it's this one, then it should be that one. Okay, however, different amino acids are cleaved at a different rate. Therefore, it's rather difficult to be able to say that, oh, the first one is glycine, second one is leucine, third one is arginine, fourth one is cysteine, and so on and so forth. So because the rate are different, it's not as if like amino degradation, whereby the rate of hydrolysis at the N terminal over here are more or less similar to every single amino acid. Therefore, you can easily identify without any doubt, this is this, that is that. Okay, so C terminal is still okay. You can still use it, but you need to do a fine control to actually know whether the sequence is correct or not. All right. So what's missing here is so what illustrated here are the methods that can be used to identify a sequence of a protein or peptides. But of course, if you have an unknown, you need to do something else, and it's a practical method, but you don't really use it at all, or well, not as much as few years or probably 50, 10 or 20 years back. Okay, so you have, as I mentioned, HPLC, mass spectrometry, NMR. So there are multiple methods that you can actually use to identify the sequence of amino acid or peptides. Okay, so summary, this is just some terminologies, enzymes, and so on and so forth. We can just have a go. Okay, some references that I've used, this is for this lecture, okay, a synchronous lecture. We will have a QR code. Next week, we have a closing QR code for all synchronous lecture, okay? Then there will be no more QR code for you guys to actually scan for this subject, okay? All right, so I think that is all for today. Thank you, and have a great day. Take care, everybody. Stay safe.
Thank you, Doctor. Stay safe,
Thank you, Doctor.
Thank you, Doctor. Take care.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.